Okay, this is sample 10-9, disc versus hoop. I'm on page 472. This isn't going to be a short video, so get a snack, get a drink, make some tea. I want to make sure that we all understand what's going on here. So back in chapter 4, we talked about conservation of energy a lot, and an object at the top of a hill, the Earth object system could convert that gravitational potential energy into kinetic energy. So we had gravitational potential energy, kinetic energy down here, and we could set them equal, right? And we'd say something like, well, mgh is equal to 1/2 mv squared. And we could solve for various things. How fast is it going at the bottom? How high was it? You guys have done stuff like that a lot. But now we're going to have two different but similar objects, a solid disc and a hollowed out, if you will, hoop rolling down the hill. And we're going to find out which one is going to win this race. And you might want to take a second and pause the video and see if you can figure out who's going to win. I will tell you it's not a trick question. It's not a tie. All right. Once they're rolling, the answer is going to be different. So go ahead and pause if you want. All right. If you paused, that's great. If not, that's fine too. We're going to figure out the speeds of these objects when they hit the bottom of the hoop, or when they hit the bottom of the hill, excuse me. So instead of writing mgh equals 1/2 mv squared this time, we have to realize that we have two different types of kinetic energy at the bottom, or while an object is rolling. We have translational kinetic energy and we have rotational kinetic energy. Okay, so instead of mgh equals 1/2 mv squared, I've got to write mgh equals 1/2 mv squared, and that is for the center of mass, plus 1/2 I omega squared. Because as we saw in the Frisbee example, we got to spend some energy getting it to rotate. So it's not going to be moving as fast as if it weren't rotating. So here's our conservation of energy statement. Okay. Now we know from the slideshow, hopefully, that to find the velocity of the center of mass, we simply have to multiply the radius times the angular speed. So what I'm going to do is I'm going to solve for omega here, and I'm going to plug it in here. So omega equals v over r. So I'm just going to make this a little bit uglier, but I'm eliminating a variable. 1/2 mv squared plus 1/2 I. Now omega squared is v squared over r squared. I'm going to tell you right now, the algebra is going to get ugly, and I'll try to be neater than that. But what have I done there? I've made things a little more complicated, but I've gotten rid of omega, and I've just got v in my equation now. So I'm going to do one more little bit of algebra so that I can factor 1/2 mv squared plus 1/2 I over r squared v squared. Now I'm going to factor out the half on this side, m plus I over r squared, and the v squared on this side. Okay, so I just did some factoring there so that I could have so that I can solve for v, because that's what I want to do, right? So I'm going to move over here, and then we're going to go to the next slide here. V squared then is 2 mgh over m plus I over r squared. Okay, yes, it's ugly, but it's just algebra. How many times have I said that? It's just algebra, and you guys know how to do algebra. So I'm just rewriting 2 mgh over m plus I over r squared. Okay, now technically you could answer the question here if you substituted or reasoned through the moment of inertia for the disc and the hoop, but I'm going to actually solve this for you, okay? So for the disc, you can go back to page 464 and find that the rotational inertia for a disc is 1/2 mr squared. So I'm going to plug that into my velocity formula here. So v squared equals 2 mgh over m plus, right, I, which is 1/2 mr squared over r squared. Okay, it looks like we're finally getting a break with the algebra here, right? The r squareds go away. V squared equals 2mgh. What do I have downstairs? M plus 1/2 m. So I have 3/2 m. Now, maybe not too surprising that the mass is canceled out. Sometimes that surprises us. We get V squared equals 4/3 gh. Therefore, V equals the square root of 4/3 gh. Okay, so that's our final speed for the disk. But it could be the speed for the disk at any point along that route, just plugging in a different, height for h. Okay, let's do the hoop. Excuse me. V squared equals 2mgh over m plus I over r squared. For the hoop, back to page 464, I equals mr squared. Okay, remember the hoop is pretty much the hardest thing we have to rotate. All of its mass is all the way from the center. So we're gonna have to literally do a lot of work to rotate this puppy. So let's do our plug and chug again, 2mgh. Now I have m plus mr squared over r squared. So V squared is 2mgh. What do I have downstairs? M plus m is 2m. So V squared equals gh, and V equals rad gh. So that's for the hoop. Compare that to for the disk, which is rad 4/3 gh. And so you can see that at any point, regardless of what h is, the disk is going to be moving faster because this has a 4/3 here and this has a 1 here. So the disk is moving faster at any point. So the disk is going to win, the race down. Now let's think about this qualitatively. The hoop has a greater moment of inertia, a greater rotational inertia because the mass is distributed far from the center. So they both get mgh at the beginning of the race, right? That's their money in the bank or energy in the bank. The hoop is going to spend more of that getting itself to rotate. So there's not enough energy left to go as fast as the disk, which didn't have to spend as much energy to start rotating. So the disk is going to be moving faster at the bottom. So just from realizing what different sorts of objects have different kinds of rotational inertia based on how the mass is distributed, we could answer that question qualitatively without even the numbers that we have here. So I'm going to find some videos and I will link those to the slideshow as well. I hope that this video helped that concept, and we'll talk more about it later. And if you want me to do this again, or if you want me to put numbers in it, I'm happy to do that. Just let me know.